All right, next in this show right here, we're going to talk about engines, what you need to do to an engine to make it worthy of a supercharger and so to withstand a supercharger. I mean, I talked about it before. You know, the idea of horsepower is to just fill the cylinder and create more pressure, and it pushes the crank around harder. Blowers do that. Problem is it creates more strain. I think I talked about before, it's like a breaker bar with a socket. If that socket will take 200 pounds of pressure and you run it at 190 pounds or 195 pounds all day, sooner or later that thing's going to give. But if you only put 50 pounds of pressure on it, the thing will last forever. It's kind of the same thing with engine internals and blower motors and stuff. They're putting strain on parts. Now some guys will take a stock motor and put a blower on it, put 5 pounds of boost to it, and it'll run. It'll run okay. It won't last real long, but it'll run okay. The reason it won't last real long is because the internal parts aren't designed for the stresses that the blower is putting on it. If you run low amounts of boost, 3 to 5 pounds, they'll be all right. Start kicking the boost up, 7, 8, 10 pounds, that stuff's not going to hold anymore. It's going to go. You need to get forged internals. And we're going to talk about all the different things you need to do to a motor and internals and stuff and cam profiles of what you want to do to make your engine compatible with a blower. We'll start off just with some internals here. We'll start off with this first connecting rod. Now, in our other shows that we do on engines and strokers and building and stuff and rotating assemblies, we talk about pistons and rods and cranks and things like that. And I'll tell you that 95% of the rods out there, actually about 98% of all connecting rods are forged. Okay, right from the factory they're forged. There are a couple that are cast. This is a particular one right here that is of cast iron. This is a Pontiac rod. Oldsmobiles, Pontiacs, and Buicks, some of those had cast rods. And the way you can tell is when you look on the side, there's a very narrow parting line right here. Very narrow. That's right from the molds of where it was cast. And you can see it's very stippled looking. That's because it's cast iron. All right? You certainly do not want to run cast iron rods in a blown motor. They will break. Okay? They're barely strong enough for anything. Like I say, most factories went ahead and used a forged rod, including all the Fords and Chevys and most of the Chryslers. So we'll go to the next rod right here. This is a early Chevy rod. It's been reworked, and I'm sure you've heard people say, "Oh, I polished the beams, you know, and I've stress relieved my rods. These were Chevy pink rods, and they're stronger than a regular rod." Nope. Chevy pink rods, the only reason they're pink is because they were magnafluxed at the factory to check for cracks. It's still the same rod that any other motor had in it, any other Chevy motor, okay? By polishing the beams right here, that does relieve stress risers and things like that, but the rod is still made out of the same material. It's not any stronger, really. And really, the weak link of a connecting rod isn't the rod itself, it's the bolts. And whoever did these rods used factory bolts in them. They didn't even change the rod bolts, and the rod bolts are what breaks. When a rod bolt breaks, the cap comes off, the crank comes around, smacks it, and throws it right out the side of the block. Rods rarely break on the beams. All right, so you know, if you're building a motor, don't settle for this kind of stuff, because that's old school stuff, and it really wasn't any better than factory stuff. If you're going to do something these days, you buy a set of aftermarket rods. These right here are forged 5140 steel. They're I-beams, they're lightweight, they're about half again as strong as a stock rod, and they're lighter. If you notice, they use a through bolt. The bolt actually comes all the way through. Rather than a stud and a nut, it's actually a through bolt. They're big shoulders, great rod, very lightweight. These things will handle 500 horsepower all day, not a problem. And they're inexpensive. By the time we work a set of regular rods and put bolts in them and profile them and do all kinds of stuff and resize them, for a couple bucks more you can buy a brand new set of these. You might as well start good. If you're going to be into hardcore stuff and the motor's going to make a lot more horsepower than 500 or 500 and up, you can opt for H-beam rods like this. This is a 4340 steel. It's a lot stronger than 5140. It's different alloys of steel. It also has cap screws that come all the way through. These are monster 7/16 inch bolts. They're huge. And the reason to make them bigger is because that's the only thing holding this cap on down here is the bolt. They're H-beam because of the cross-sectional area right here is shaped like an H. If you cut it in half and looked at it, it looks like an H. Where these I-beam rods, if you cut them in half, they look like the shape of a capital I. These are excellent rods for that kind of horsepower, 500 and up. The next thing are pistons. Most stock engines have cast pistons. Cast pistons and blowers don't mix. There are other pistons out there now, hypereutectic pistons, and they're okay. We don't prefer to put them in blowers. In fact, we don't here at Badass Racing Engines. We don't put them in blower motors because they will break. You always want forged pistons in a blower motor. You know, and you'll find pistons like this. This is your typical sealed power, excellent piston, forged, a good piston. They're a little on the heavy side, but they're not very pricey, and this is a good piston to go with. But I wanted to show you something. The reason I chose this piston is because this is what you don't want with a blower. This one has a dome on it right here, and that's not something you're going to find in a blower motor. What you're going to find inside of a blower motor is a dish piston, much like this one right here. And the reason it's got a dish is because we want to lower the compression. And the compression ratio on a blower motor ideally is between 8 and 9 to 1. On race motors, we get them down to 7, somewhere around 7 to 1. The reason we do that is because every time we shove more fuel and air in there, the effective compression goes up. The static compression stays the same. If this is an 8 to 1 piston, then that motor has 8 to 1 compression. But as the more boost we push into that motor, it makes the effective compression ratio come up quite a bit. And the cylinder pressures are tremendous. So the tops of the pistons need to be, the whole piston basically, but the tops need to be very strong, very durable to take those pressures pushing down on it and the heat. And a good forged piston, a good lightweight forged like this is an SRP piston. You see right inside there it says SRP. It's a good lightweight, actually good bang for the buck piston. That's a good choice for blower motors. Same thing on crankshafts. Now your stock cast crank can withstand some boost on blowers. We've seen stock cranks in blower motors last quite a long time. I mean, if you're going through the trouble of building a blower motor, though, specifically for something that's going to have high horsepower, then don't start with a cast crank. I mean, that's crazy. There are aftermarket cranks. This is an Eagle crank right here. This is 4340 steel. They're very inexpensive. There's also 4130 steel cranks. They're a little less expensive than 4340, a little bit lighter. There's different alloys for different tasks out there, but you might as well start with good stuff because once one of these components goes, it takes everything else with it and you lose everything in one shot. It costs 3 times as much to do it the second time around. So it's better to do it once, be done with it, and not have to go back and redo it again. All right, before I go on here, I thought I'd go ahead and show you a hypereutectic piston and what that is. I said, stock engines come with cast pistons. A hypereutectic piston is a cast piston, and that's a misconception a lot of people have. They think they're forged or a lot stronger than a stock. They're not. All hypereutectic means is it has a higher silicon content to it, which bonds the aluminum molecules a little tighter together. Yes, they are stronger than stock pistons, and they're good for most performance applications, but for superchargers or a good shot of nitrous, no way. You got to have forged. But this is a hypereutectic right here. This is a fully machined, really nice one. This is the Keith Black Signature Series. They are a good piston, nothing wrong with these, but I wouldn't recommend them for a supercharger, especially something that's got a lot of boost. If you're running low boost and you know you're going to stay at low boost, then one of these would be fine. But if you're going to run into high boost, 10 pounds or above or anything like that, or 8 PSI and above, I really wouldn't want to run one of these. It's not what I would recommend out of my shop. Let me kind of explain what happens to these. The pressure on top of the piston right here gets so great and the heat is so great that cast pistons, they're brittle. Any cast item is brittle. If you take a piece of cast metal and you force it one way or the other, it'll snap, it won't bend. Same thing with the top of a piston, they'll actually crumble. And if you take this, if I took a ball peen hammer and I smacked it right in the middle here, especially a stock piston, it would just crush. You'd poke right through and it's brittle, it would crack and break. This right here might take a few hits of it and it would also finally break. If we took a forged piston though, like this, and I smacked it on top with a hammer, it would just dent because the molecules and the way the forging process is and all the molecules and the granular structure of the aluminum, they're a lot tighter and the grain stays together and it makes this almost a pliable metal. I mean, what I mean by that is if I smack it with a hammer, it'll actually dent and move. Even though aluminum is brittle in itself, it's not like steel. It won't really bend and things like that, not as well as steel, but it'll actually dent and move around before it breaks, and they take a lot more abuse than a cast piston. So with that, with pistons and everything, I've said this before, horsepower makes heat. Whether it's a blown motor, a nitrous motor, or a naturally aspirated high horsepower motor, horsepower makes heat. There's no getting around that. Blower motors have specific things you have to do to them. This is why you can't just take a blower and pop it on a stock engine and expect it to work. I've talked about cam profiles, compression ratios. I mean, if you've got a high-performance engine from the factory that's got 10 to 1 compression or 10.5 to 1 compression, you don't want to put a blower on that. You're going to have detonation problems really bad. You're going to have pre-ignition. The cylinder pressure is too high when the piston comes up and compresses. There's too much static compression there. You can't put any boost to it to make any power. So with horsepower making heat, there's things that we have to take into consideration. Metal expands. I mean, if you got a metal part that's stuck, what do? You heat it up with a torch until it expands and it loosens up and you can take it apart. Well, it also works the opposite when you're captured inside of a cylinder. You've got a cylinder bore and a piston sitting in that cylinder bore, okay? As the piston's sitting in that cylinder bore, it can't really move, all right? So the cylinder expands at a given rate, all right, because it's cast iron. The pistons are aluminum. They expand a lot more than cast iron. So as these expand and get tighter, 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 the clearances between the piston and the cylinder wall, called the piston side clearances or piston skirt clearances, those start getting smaller and smaller and smaller. Well, the more horsepower you make and the more boost you put on a supercharger, the more fuel you put inside the motor, the more these things expand. Pretty soon they expand so much they got nowhere to go, and they basically seize up. You'll embed the piston right into the cast iron cylinder, and you basically weld the two together. Well, the same thing happens with piston rings. Piston rings have end gaps, and that's this little area right here. When the ring is compressed and put on the piston, you've got a gap right there. Well, these are designed to work at certain cylinder temperatures. When you go adding a blower to it or anything like that, any type of forced induction, again, heat expands the metal. Well, when the ring gap's at a given area and a metal expands, expands, and expands, it butts that ring together and it has no place to go. Pretty soon there's no ring gap. Guess what it does? It'll blow the top of the piston right off. This whole piece right here on the side of a piston will break off. It could be anywhere, but that's what happens when you see the top of a piston blown off. That's because the ring gaps butted together. It wasn't ample gap there to withstand the heat, because the metal of the ring could only take so much before it butted itself together and blew the top of the piston off. So things like ring gaps and piston skirt clearances need to be taken into consideration, which means when you're doing engine machining, you're honing the cylinders out, we need to hone an extra 1,000th or 2,000, sometimes 3,000ths more piston skirt clearance in there than what we would normally have. Ring gaps, sometimes as much as another 10 or 15 thousandths gap. On hypereutectic pistons, you already have to expand the ring gaps just because of the nature of the way they throw the heat back up into the cylinder to make more horsepower. It really heats up the ring gaps. So if you look at like the instructions of a Keith Black piston, it'll say to open up the ring gaps by like 0.065. You times the bore by like 0.0065, which makes it like a 26 thousandths more on a 4030 bore. You got to expand the ring gap from like 19 thousandths to like 26 thousandths. Then if you're going to go to a supercharge, you want to bring it up to about 30 thousandths gap. That's quite a bit, because a factory ring gap's like 16 to 18 thousandths. Well, 30 is almost double. Okay, so that's a lot. We're not talking 1 or 2 thousandths on a ring gap sometimes. Sometimes it's quite a bit. So obviously if the rings didn't have a place to go, they're going to butt together, they're going to break things, and things are going to happen. And that's not what you want to have happen in a supercharged motor. So those are some of the clearance problems that you run into. But now that you know that, you know a little more on the piston skirt clearances and open up the ring gaps. And most of the ring manufacturers will tell you where you need to go. They'll give you a little chart when you purchase the ring. It'll tell you how much more to open up the gaps for towing or for naturally aspirated use or race use or supercharged use or nitrous. They'll tell you where they want that gap at. And also on rings, always moly rings. A general cast iron ring just can't take the pressures in the cylinder from a supercharged motor. So you always go to moly. Now there's single moly, there's double moly, there's plasma moly, there's iron ductile plasma moly. Basically a single or a double moly ring is fine for a medium to mild supercharged motor. When you start getting up into the heavier duty stuff, you're going to be running high boost levels. You're going to want to run what they call an iron ductile plasma moly ring. It's just the type of coatings they put on it and type of material. When you really get up into the hardcore stuff, maybe some gapless, some total seal gapless rings might be a good choice. We use those in some even naturally aspirated motors. That's a good ring. It just depends, it's all preference. They're all good. There's not too much junk out there, because it isn't out there very long. If it is junk, no one uses it. But that'll give you kind of an idea of what's going on inside the motor. All right, another thing you want to do for internals to make things strong, you know, the blower drives themselves, where the crank drive pulley turns the belt, it turns the blower. Blowers have quite a bit of drag. I mean, those rotors don't spin easily. So when you throttle the motor up, it's putting quite a bit of load on the crank and on the harmonic balancer or the crank hub that's turning that blower pulley. Well, factory harmonic balancers come with a single keyway. They come with a standard 3/16 keyway. Well, what can happen is that because of the load that the blower puts on that, you can either split the keyway. Here's one right here. They tend to split right in the corner right here or right here, and that's not good. So you always want to use like a steel hubbed harmonic balancer, something with a steel hub or at least a nodular iron. But another thing you want to do on big blowers is you notice this one has twin keyways. It's got two. That also means the crankshaft was cut and it's got two keyways in it. And what that does is it makes it less amped to shear off a Woodruff key on there while it's trying to turn that load of the blower around. And you can also purchase these. We cut this one. This is actually one that was run. We took it off. We're going to put another one on. But this is one that was run. But you can purchase them that way for Superchargers, the aftermarket companies that make, you know, the steel SFI approved harmonic balancers. You can purchase them between keyways. And any machine shop can put a second keyway in your crankshaft snout. That'll ensure that you don't shear anything off. Mild motors, you really don't need that. If it's just a, you know, one of the small Y-end blowers or the 177s or something, or a mild 671 with 5 or 6 pounds of boost, you don't really need to do that. But you're going to bump the boost up and run a big, heavy supercharger with a big drive. You might want to do that so you don't blow the harmonic balancer off. All right, other things we need to talk about here to make your engine strong and compatible with a supercharger are some of the other internals. What are some of the internals? Well, how about this? What are the things holding the internals together? The bolts, okay? These right here are main bolts. This is a factory main bolt right here. This is what's been in an engine for, oh God, who knows how long, how many years, 20, 30, 40 years. It's been torqued at like 70 foot-pounds, which means it's stretched. It's been heated and cooled, heated and cooled, heated and cooled about 10 million times, which means the temper of this bolt right here is not very strong. It's, you know, might not hold the main cap in place very long. So always you want to change main bolts and head bolts and things like that, and connecting rod bolts. This one right here is an ARP bolt. They come with parallel ground washers. The tensile strength of this is like 190,000 psi. It's way stronger than a factory bolt. The alloys of it are a lot better than a factory bolt. I mean, to the naked eye, a factory bolt might look fine. You might take your engine apart and go, hey, the bolts look great. You can't tell by looking, okay? You don't have x-ray eyes, all right? The only way to find out if a bolt is bad or not is to put it on a Rockwell tester. And guess what the Rockwell tester does to find out if it's good or bad? It breaks it. And it goes, whoa, that one broke it a lot. That was a strong one. Or, boy, that one let go quick. That was a weak one. So, I mean, unfortunately, you can't test it and then put it back on. Best thing to do, look, it's cheap life insurance. The only thing holding your motor together are the bolts. I mean, literally, okay? What holds everything together? Bolts. They better be good ones, especially when you're talking a supercharged motor, any type of performance motor, because if they're bad, things are going to come apart, and that's not a good scenario. So let's look over here. We're going to talk about, speaking of beginning, we're talking about main bolts and things like that. I'm sure you've heard the term 4-bolt main. Guys going, hey man, I got a 4-bolt main block, or mine's a 2-bolt main. All right, we're going to talk about that. This right here is a Ford 351 Windsor block. It's destined to become one of our 408s. We've got some 408s that we do for a lot of people. Most Ford blocks, in fact, almost all Ford blocks are 2-bolt main blocks. Okay, and I'm going to explain that and what that means in a minute here. This one looks a little different because this has one of our aluminum main supports on it. It's made out of billet aluminum, and what it does is it ties all the main caps together. All right, let me just kind of explain what we're talking about here on mains. We'll come over here to this Chevy motor right here. This is a 350 Chevy block, soon to become a 383 cubic incher, and these are the main caps right here. This is what holds your crankshaft in place. All right, all the bearings, your crankshaft bearings fit right inside here, and a crank sits inside. And the only thing holding the crankshaft in are these main caps right here. If these main caps wiggle or move, or the bolts stretch or break, and they come off, the crank's coming out. And think of it like this. A supercharger is putting a lot of pressure down on the pistons, which is putting a lot of pressure down on the crankshaft. And the more strength you push down on that, you've got the pressures pushing down on the pistons, it's trying to push the crank out the bottom of the motor. Well, the only thing holding the crank in are these main caps and the bolts. Okay, so it's better to have a 4-bolt main block. Well, let's show you what a 4-bolt main is. It's got 1, 2, 3, 4. 4 bolts. That's a 4-bolt main. It means all it means is it's got 4 bolts holding the main cap on. Just means it has double the clamping power or clamping pressures or clamping strengths than it does on a 2-bolt. Okay, and they're that way all the way across on the center ones. Hardcore race blocks have them from the front one all the way to the back. All of them are 4-bolt. Factory blocks didn't. The back ones and the front ones, those are all 2 bolts. And they just had the 4 bolts in the middle. So that's what a 4-bolt main is. Well, unfortunately, Ford only have 2-bolt mains. The difference was, though, Ford used larger bolts. They used great big main bolts. They're a lot larger. In fact, they dwarf a Chevy bolt. So it's not that a 2-bolt is weak. I mean, if we look at this right here, look at this front main cap. This is twice as thick as that Chevy cap. That's a big, beefy cap. So don't let the term 2-bolt or 4-bolt main confuse you or scare you, because I know your Chevy lovers out there going, yeah, see, I told you, man, Fords are no good. They're only 2-bolt main. Well, Ford's got great big old main bolts holding them in. In fact, these are studs. We've converted this to studs. They're twice the size of a Chevy. The main cap is twice the size. And mind you, the bolts hold the main cap in place. But if the main cap lets go, the crank's still coming out, okay? So these are also as big. So don't go getting off your seat yet, Chevy guys. All right. So same thing with this. You know, the 2-bolt main block needs to be strengthened up. What this main support does is it ties all the main caps together. So basically, say this center main cap right here, if it wants to wiggle or move or pull off, it can't. It's dispersing its load across all the other main caps. So if it's going to move, it's going to have to take all the others with it. Can't do that. Essentially, it turns this motor into a 9-bolt main, because now there's 2, 4, 6, 8, 9 bolts holding the crankshaft in place. So any one main cap that wants to move, it's going to have to take them all with it. And it also prevents main cap walk. The more stress you put on a block, sometimes the main caps themselves, they can wiggle back and forth a little bit, and what they call block deflection. The block actually moves and flexes a little bit. It's not good to have that, but when you're putting tremendous boost to a motor and you're making lots of horsepower, things give a little bit, and that kind of stuff happens. Main supports prevent that. Unfortunately, we don't really make these for Chevys. These are pretty much just for Fords, and because we already have the 4-bolt mains on Chevys. And when we convert a Chevy to studs, or we also go to billet steel main caps on those, that strengthens that up, and we end up with a lot better and stronger block. But that just gives you an idea on the bottom end of strengthening it up so you don't have a crankshaft problem. So while we're on the subject of bolts, we'll talk about head bolts. Now mind you, if you're rebuilding your motor and you're going to put a supercharger on it, take your old head bolts and just throw them out, okay? Again, they might look good, but they're not, all right? Unless they're brand new or they've only been used for a very short amount of time, you don't want to mess with them. Make sure you get yourself something good, like a set of ARPs or something like that. Keep in mind, the only thing holding the heads against the block are the head bolts, and if they're not good and they're not keeping their clamping pressure down, you're going to blow a head gasket, okay? Now speaking of blowing head gaskets, let me show you where the head bolts are here on a Ford. Because supercharged motors or supercharged Fords have a little problem with head gaskets. That's easily remedied, but they do have a little problem. Let me explain why. Fords only have 10 head bolts, okay? So on any bank of the motor, on the left bank or the right bank, there's only 10 head bolts, okay? And if you look right here, here's a cylinder, and the very end we have 2, and right in between we have 2. Notice this whole span right here has nothing in there. All right, that presents a problem as far as head gaskets. Chevrolets don't have that problem. All right, Chevys have 17 head bolts. All right, so think of that. Fords have 10, Chevys have 17. That's 7 more. It's almost twice the amount of clamping pressure. So we come over here to a Chevrolet. This is a small block Chevy. Look at them all. 1, 2, 3, 4, 5. It's almost completely circled. So that head gasket, the fire ring on that head gasket is completely clamped down and is held in place. You can't, it doesn't blow as easy as what a Ford does. Okay, now mind you, we go back to the same theory. Again, Chevrolet uses smaller head bolts. Ford uses great big 1/2-inch ones. Chevys use 7/16, which are a lot smaller. So even though Ford has 10 head bolts, they still have the thicker bolts for clamping. But Chevrolet has the advantage of going all the way around the cylinder. I mean, that's almost completely circled. And with almost twice the amount of head bolts, it holds that head in place a lot better. You're less apt to blow a head gasket. So when I show you a head a little bit later here, we'll show you how to remedy the problem with Fords with an O-ring. All right, so let me show you those little O-rings I was talking about on the Fords. This is a typical small block Ford head right here. And you can see right here, there's actually grooves machined around each combustion chamber. And what that is, a machining process that we do, and there's a specific head gasket made for this called a Felpro 1006. They're called a lock wire head gasket. What that means, in fact, here's one right here. It's a head gasket, and inside of it is a stainless steel wire that doesn't get compressed. And what happens is, these are receiver grooves. So when this head gasket is put in place on here, and you torque that head down, what happens is that, you know, we probably all know, or most of you probably know that when you torque a head down, the head gasket squishes, it compresses. Well, what happens is the wire inside here does not compress, and it goes up inside those grooves. Creates like an O-ring seal. That's a great idea for supercharged motors, nitrous motors, stuff like that. They don't make these for Chevys because Chevys don't have that problem. They have the 17 head bolts. They have all the bolts all the way around. They only make these for the Fords. One thing too, I just want to say, I did say that Fords have 1/2-inch, head bolts. They got big head bolts. Not all of them do. 289s and 302s have 7/16. But you can certainly take 1/2-inch head bolts and have the block machine to accept 1/2-inch head bolts. So you got the larger bolts. So that right there alone, the 1/2-inch head bolts plus these Felpro lock wire gaskets, that head gasket's not going to go anywhere. I mean, they'll stay right in place. Now you can buy heads like these. Edelbrock makes some that are already machined for this. It's just an option that you can purchase. As a matter of fact, Edelbrock's, the Victor Junior heads, that they're supercharger ready, they're the 70cc combustion chambers. They come already O-ringed. Those are a concept of badass racing engines. You look in the Edelbrock book and you'll see that in there, concept of badass racing engines. So yes, that is something you can purchase, and so you don't have to have anything sent out and machined. And we're talking about cast iron and aluminum on heads. You know, you can get the Fel-Pro Lockware gaskets already machined in aluminum heads, or you can already have your cast iron heads machined for it. I don't know if I would do that though. Cast iron doesn't go real good with superchargers. And what I mean with that is horsepower makes heat. Okay, when you fill a cylinder with more fuel and air, you got higher combustion temperatures. And cast iron does not cool down very fast. You're probably bound to get detonation, or what they call pre-ignition problems, pinging problems basically, that go on with cast iron heads. Cast iron heads are not a good idea with blower motors. You definitely want aluminum. And by the time you machine grooves in these, you put screw-in studs in them and guide plates and port them and do all kinds of things to really make it worthy and compatible with a supercharger to get the most out of it. For a couple bucks more, you could have got aluminum. They're lighter, they run cooler, they're 2000s technology, they're redesigned, spark plug locations are slightly moved, things about them. They already come with all the cool stuff, and they're really not that expensive, and you can get them all set up and ready to rock and roll. The cool thing with aluminum is, though, if I heated this head up right here to 500 degrees and came back, say, 15, 20 minutes later, it's still smoking hot. I mean, it doesn't cool down very fast. If I heated an aluminum head up to 500 degrees and came back 15 minutes later, it's probably cooled down. I mean, I could probably touch it. What has to do with blowers on that, though, is the combustion chambers right here. When the flame inside, when a spark plug ignites the cylinder flame, this whole area, I mean, the whole head gets hot, but this area stays hot. So when the next time that cylinder wants to fire, there's things in here that could be glowing cherry red just because of the heat that's going on in there. Well, that can pre-fire the cylinder, you know, fire it before the spark plug does. It's called pre-ignition or detonation. And man, all kinds of crap happens when that goes on. I mean, head gaskets blow, you can break pistons and stuff. So when you're building a blower motor, cast iron heads are really not a #1 choice for that. All right, we talked about, you know, can you put your blower on a stock engine? Well, how about if you already have a built motor that's, you know, got forged pistons in it and it's a bumping and grinding motor already? Can you take your intake manifold off and just take a blower and bolt it on there? Probably not, because chances are your compression's a little higher than it needs to be, your cam profile is probably wrong, and that's what I want to talk about right now is, you know, you can't put a blower on a radical motor usually because of the compression and cam profiles. Usually everything else is plenty strong, the crank and rods and stuff like that, if you already got a good motor with good heads and everything on it. But blower cams, they're on the mild side. They have very little overlap. The lifts and durations and stuff, that doesn't have a whole lot to do with it. Of course, the bigger, the more the lift and the little bit more duration that they have, the more power they'll make. But there's something of the overlap and what they call the lobe separation angle. And blower cams tend to have a wider lobe separation angle. You know, you look on hardcore race cams, you know, they'll start getting into 104 lobe centers or 106s and, you know, 108s and stuff like that. That's not a very good lobe separation angle for a blower. Usually you'll find if you look in any catalog, any of the name brand cams out there, and you look in the catalog, all the blower cams have lobe separation angles, or some people call them lobe centers, of like 112 and 114. That's to help build the pressure up in a cylinder. I mean, again, the obviously thing behind horsepower is building cylinder pressure. When you don't have the correct camshaft and you got a radical cam, put it this way, if your cam's bumping and grinding, you know, and it's a lopey cam, it's probably the wrong camshaft for a blower. What will happen with cams like that is they won't build up the boost, and all the boost goes out the exhaust. And that's not good. We're not trying to blow the boost out the exhaust. We're trying to build it up as pressure inside the motor. But it's also not all about pressure. We have to kind of think about this for a minute. I would rather see 5 pounds of boost at 3,000 CFM than 30 pounds of boost at 500 CFM, meaning flow is what makes the power. The object is to flow fuel and air into the motor, get it to burn and expand and push that crank around and get it the hell out of the motor. That makes horsepower. Backing up boost behind the intake valve and building up a bunch of boost in the intake manifold, that's kind of the name of the game, but that's really not what you want. I mean, that way when the intake valve opens, you know, fuel and air force their way inside there. Where naturally aspirated, it draws in from the vacuum of the motor, and big cams don't have that much draw. That's why big cams on naturally aspirated motors, they don't come in until 3,000 RPM. You know, a lot of guys will say that. You know, my car goes real fast once it's above 3,000 RPM. It's because of the cam profile. Blowers, they come on right now. So that's kind of what I want to talk about like that is on cam profiles. You want to be sure that if you're not sure about getting a camshaft, be sure to call a cam manufacturer, talk to their tech department, and get the correct cam profile for the amount of boost you're running and amount of cubic inches to utilize the blower, because you certainly don't want to spend all that money on something like that and have it be a bloomin' turd because it's just not compatible with all the other components inside the motor, and especially the compression also. You don't want any high compression or anything like that. Mostly what you want in compression is 8 to 1, 9 to 1, that's about it. If you got 10 to 1, you're not going to be able to run any boost. 11 to 1, forget it. The only motors out there that run 11, 12, 13 to 1 compression with the blower are alcohol motors. So blown alcohol motors, we start at 12, 13, and 14 to 1 compression on alcohol motors. And that's just because alcohol in itself doesn't really burn. So you need to already compress it even before the boost goes in. You got to compress it to even fire it. Because put it this way, how's an alcohol motor supposed to idle if it has 9 to 1 compression? Alcohol won't even burn in I don't think a 9 to 1 motor even really run on alcohol, especially an 8 to 1 motor. It's just not going to happen. It needs 12, 13, 14, just to give you an idea. Race motors with alcohol, they're 15, 16 to 1 compression. Some I've seen as high as 17 to 1 compression on naturally aspirated alcohol motors. So you have to have what they call static compression, enough to sustain the engine to run. And a regular gasoline engine, it'll run on 8 to 1 and 7 to 1 compression, and that allows you to stuff more boost in there to bring the cylinder pressures up without getting too much detonation. But that's a little bit on cam profiles and compression. Just make sure they're matched to what you're getting. If you're not sure, Wyand, Blower Drive Service, all the blower companies out there, Vortec, everybody out there, they all have tech lines. They're all glad to help you on that kind of stuff. And you're certainly not going to learn everything out of this video right here, but it'll give you a good idea of what you're looking for, what you need to run, and how things work, and general ideas like that, so you know what to get and what you're up against and what you can do and can't do. And hopefully that helps you out a little bit. All right, another question I get asked all the time, people say, hey Aaron, I want you to build me a blower motor, but you know what, I can't afford the blower right now. Can I just get the motor built and I'll add the blower later? And I want like 450 horsepower, then I want to put the blower on after that. That's a tough one, okay? Put it this way, we already just talked about cam profiles and compression, all right? A mild cam profile and low compression, even if you got good flowing heads, it'll make some good horsepower, but you need the cylinder pressure and a cam profile to support that kind of power. And making 450 horsepower in, say, a 350 Chevy, that's doable. It's a pretty radical motor. I mean, we have 450 horsepower street motors that run on pump gas that are single carbureted, but it's a bumping and grinding motor. You're certainly not going to tame one down for a supercharger and have that kind of horsepower and then put a supercharger on it later. So what I'm getting at is, yes, it's doable to build a motor like that, but you have to realize that it's not going to make the same kind of power as if I built a motor that's not designed for a supercharger with higher compression and a more radical cam profile to make the kind of horsepower it needs to make. So with that, if I build a blower motor and it doesn't have the blower on it, you're not going to have the same kind of power as if I'd built one without the blower, or not designed for the blower. So yeah, it's doable, and you can add the supercharger later, but don't expect the same kind of power you'd have out of another motor, that wasn't designed for the blower. And yes, I understand the blowers are expensive, but it's better just to build the motor and do it, because one thing is too, if you can't afford the blower till down the road, down the road might come quite a few months later or maybe even years later. Well, by that time, the bottom end of the motor is half whooped. You don't want to put a blower on top of a motor with a lot of miles on it, because we talked about cylinder pressures and rings and the ring gaps and piston skirt clearances and stuff. Well, all that stuff's set up to be designed for a certain amount of heat and cylinder pressure inside the motor. Well, if it's not there, guess what? You're going to have blow-by. The motor's going to smoke. It's going to use some oil because you've got all these increased clearances. It's also going to be noisy, especially when it's cold before the pistons have heated up and expanded. So it's not a very happy motor when it doesn't have the blower on it. So you're driving something around that, you're like, hey man, it's using oil or it smokes a little bit. Yeah, because it's waiting for that cylinder pressure, all the blower pressure to come in and all the fuel to go in there to warm that stuff up and get it in its normal operating temperatures, which are a lot higher with the blower than they are without the blower. So yeah, it's doable, but it's not really a recommended thing unless like next month I'm going to put the blower on, or very shortly down the road, 1 or 2, 3 months later. If it's going to be any longer than that, I don't know if it'd be worth it or not. And on normal engines, we talk about heads, and the old term, bigger is not better when it comes to heads and cams and carburetors and stuff like that. On supercharged motors, that really doesn't ring true. But Small heads and small runners work real well too. The reason being is pressure makes flow and flow makes volume. So we go over here and look at this. This is just your stock head right here, at stock ports, stock valve sizes, and being that superchargers put pressure out, it will make the flow. I mean, these heads will flow a lot more than what they would normally aspirated. So if you have, stock heads, it's not a bad choice to use. It's better if you don't have cast iron heads though, like maybe the small aluminum heads. A lot of cars these days come with aluminum heads. Some of the late model Mustangs and Camaros and things like that. That's a good choice. You can put a supercharger on cast iron heads. It's not the greatest choice, but you can do that. Come over here. This is a 210 cc head. So the intake runners right here are 210 cc's, where a stock one, such as these, are about 140 cc's. So there's quite a bit of difference. On a naturally aspirated street motor, especially in a heavy car, or if it's not geared down in the back, if you don't have 373s or 411s or anything like that, these heads might be pretty big. On a supercharger, though, it will create velocity inside here because of the pressure. So it's supercharger is kind of the best of both worlds. They'll make small runner heads work. You can also use large runner heads. Obviously, if you got large runner heads, you're going to make more power. That's kind of the beauty of that it will work real good. And you will have good bottom end throttle response and bottom end torque with a supercharger. If it was naturally aspirated, you wouldn't, because you got to get the engine to rev up and get the camshaft working and things like that. In supercharged motors, the cam profiles are a lot milder, and you get better low end throttle response and low end torque. And trust me, boost does make volume. And pressure does make volume. If you don't believe me, we can look right here. Here's a typical blowgun. Look how small the orifice is on this. It's pretty tiny. It's just a little teeny thing. But there's 100+ pounds of pressure on here. Pressure makes volume. And you don't believe me? That'll say it right there. Okay, let's talk about ignition systems. When you're supercharged, ignition and timing is very, very important. A little too much timing, and boy, you can have detonation and break a piston or blow a head gasket real fast, or even worse, really wipe out the motor. In some of the other videos that we've done, we talk about elaborate ignition systems aren't usually needed for most normally aspirated motors, but supercharged motors and nitrous motors and engines like that, it's a whole different story. Keep in mind what a blower does. It compresses air and forces it inside the motor. Well, you have to maintain a certain air-fuel ratio of about 12.5 to 1 on a supercharged motor. That means, 12.5 parts of air to every part of fuel. That's pretty rich, okay? And you need to light that. Well, that's just on a street motor. When you get into race motors like alcohol motors or fuelers or even blown gassers, and you got, race gas going in there, that's a very dense, wet charge filling that cylinder. Well, it's hard to light it with just a basic ignition system. There's not enough voltage and not enough amperage there to ignite that. And in fact, fuelers and alcohol motors, they get what they call flame out. And what that is there's so much fuel going into each cylinder. It's like pumping almost raw liquid fuel in there. It's hard to light it. You ever see a fueler that got twin magnetos and twin spark plugs, okay? That's to help light that cylinder, because it's so wet, a lot of times they won't light. So a good ignition system is essential on a supercharged motor. Let's look at a couple right here. This is a real good distributor. It's billet. It's got a magnetic trigger inside. You can get these self-contained, where they don't need a separate box or a control box, or you can get them where they use the control box, like a multi-spark discharge. Those are real good boxes too for supercharged motors. Real good to have. I'll come over here. This is your standard General Motors HEI distributor. This is an aftermarket one. It's made out of billet. It's upgraded a little bit here and there. You can use these too. The problem is, though, you can only use these on some of the little teeny blowers, some of the wind 177s or 144s, some of those the small blowers like that, because the diameter of this just won't fit behind like a 671 or an 871. You're just not going to fit it back there. So you need to go to a small diameter distributor. And this is fairly small in diameter. There are even smaller diameter ones than this that they make that are specifically small diameter, that are designed for the backup blowers, because there's just really no space back there. A lot of race motors use magnetos too, and they're actually a very small diameter. So let's talk about timing. There's several types of timing on an engine. You have initial timing, what they call idle timing or initial timing. That's when you set it with just a timing light and you look at your crank and you're 6 or 8 degrees advanced on the crank. Then you have a mechanical advance that's inside the distributor. Those are the weights inside that actually mechanically advance as the RPM comes up. And then you have vacuum advance right here. Okay, so there's 3 different types. It's very important that you know where your total timing is. And in performance motors, we never look at initial advance. I mean, we don't bother with that. We're only concerned with total, what the total timing is or total advance. And what that means is every distributor has mechanical weights in it. Some race distributors, though, when we set them up, we do what they call a lockout distributor, and that has no mechanical advance in it. I mean, if you hit it with a timing light when it's idling, it's at 36 degrees on the crank or 34 degrees at the crank. I mean, that's how much advance it has when it's idling. It's all in. There's no movement inside the distributor. Normal distributors, though, in most street motors, they have mechanical advance. That way it's easy to start, especially for easy starting with higher compression motors and things like that. You do want the mechanical advance. But we talk about the total advance. What that is, that's how much movement is inside the distributor. Say this distributor has, 25 degrees inside of it of movement, okay, of mechanical advance. If we're trying to achieve, say, 35 degrees of total, that would mean 25 in here, and we'd want 10 degrees of initial on the crank. 10 degrees plus 25 is 35. Now, the magic number for most performance motors is between 34 and 36 degrees total advance. Supercharged motors, you want to lay them back a little bit. Usually around 30, 32 degrees is good. Sometimes you can get up around 34, but if you're running higher boost levels, anything above 6 or 8 psi, you're going to have to start laying it back, back down to around 28 to 30, 32 degrees of total. So it's really important that you get a specific timing light for that, or have someone do it for you that knows what they're doing about getting a total advanced timing. A lot of supercharged motors don't use vacuum advances. Most performance motors don't use a vacuum advance. And that's a whole different story. It's only there really for part throttle economy. So we're not even going to really talk about that much because blower motors aren't into part throttle economy. So let's talk about timing itself. There are some helpers here for timing. We have a box right here. It's made by MSD. It's called a Boost Timing Master. And what this does, this is an ignition controller. It makes a multiple spark discharge. That means the spark plug actually ignites several times in one shot. But the difference between this is there's a little port on the side right here. And what that is, we take a port off of the supercharger, like say the blower boost line, and we plug it right into here. And what that does is, as boost comes up, we can adjust this with a controller right here. There's a controller. We can set the amount of retard that this does. And we talk about that. When the boost comes up, when RPMs come up on the engine and a boost goes up more, you're going to want to start laying the timing back. You don't want to advance the timing at a high RPM. The whole name of the game really is you want as much advance as you can possibly use without detonation problems on a low RPM to get you out of the hole and get you launched off the line. When the engine starts coming up in RPM, you want to start laying the timing back because that's when boost comes in and cylinder pressures start increasing because of the cam profiles and things like that. So what this does is it starts backing the timing back as the boost comes up. And we can control that between nothing or 1 or 2 or 3 degrees for every pound of boost. So if we're at 3 degrees right here and we have 1 pound of boost going in this, it'll lay the timing back 3 degrees. So therefore, if we're at 36 degrees total advance, when 1 pound of boost comes in, we're back down to 33 degrees. And as boost comes up, at 10 pounds of boost, it'll knock this back 30 degrees, which would be too much, but we have control over it like that. And basically the magic number, like I say, for supercharged, you want to be around 32 degrees, somewhere's right in there of total advance. Now there is another ignition system too I can show you here. This is a universal ignition. This is also made by MSD. This is for like if you have points or you have a factory electronic ignition, you could use something like this right here. It takes the place of using a special distributor. You can use a factory distributor with this. And what this is, it's not only an ignition system, it's also a manual timing control. And this mounts inside your car. And as you're driving and you get on the throttle, you can actually lay the timing back anywhere from 0 to 15 degrees while you're on the throttle. So when you launch off the line, you might want your full advance, and you can mount this by your shift lever. And as you go and you need a little bit more retard in the ignition system, you can lay the timing back a little bit, and it helps the motor. So you really don't want to over-advance the motor because you can really have detonation problems and really damage the motor. All right, another aspect of ignition are spark plugs. You know, there's all kinds of different types of spark plugs and heat ranges and things like that. You know, general rule of thumb, performance engines like to use a colder spark plug. And that just means what temperature the spark plug itself is going to run at. You know, there's a misconception that you've probably heard out there that, you know, if you run too hot of a spark plug, it'll make the engine run hot, and that's wrong. Spark plugs don't have any heat to them, you know. I mean, they're just a place for the spark energy to jump a gap, and that's all it's for. The engine heat heats the spark plug, not the other way around, okay? So a hot spark plug or a cold spark plug is not going to make your engine run colder or hotter. It has nothing to do with that. The engine's going to run at whatever temperature the combustion inside with the cylinder pressures and the fuel, the compression, all that kind of stuff, and the heat that's happening in the cylinder is how hot it's going to heat the spark plug. A cold spark plug, though, is more of a solid core inside, and it doesn't allow too much heat to build up inside the plug. So let's look at a couple plugs right here. These two plugs right here are very similar. What they are, though, is one's an extended electrode and one is a standard electrode. And what that means is, you know, on a lot of supercharged engines, you don't want to use extended electrode spark plugs. And that's this one right here. This one right here is an extended electrode. You can see it actually sticks up a little higher than this one. And reason being is you got high cylinder pressures and high heat in a supercharged motor. And that electrode, the very tip of this electrode right here, this tip can start getting overheated and start glowing. Well, then you have pre-ignition or detonation problems. So a lot of times on supercharged engines we'll run non-extended tip electrodes. So let's go on down the line. Spark plugs also are not just for heat ranges, they'll also show you jetting. And if you have too cold of a spark plug, what will happen is the heat of the plug doesn't get warm enough to burn off carbon deposits or oil deposits that build up on a plug. And remember, supercharged engines have wider piston skirt clearances, wider ring gaps, and things like that. So you are going to get a little bit of oil up in there, and that's normal, that's okay, because you have to have some place for that metal to expand and have a place to go. But with that, though, you got to be careful of the heat ranges and jetting on a spark plug. If you get one that's too cold, it could look like this. Okay, that's too rich. It's all black. It's all carbon on there. That engine was either running too rich or the spark plug is too cold. So when you're jetting for superchargers, you got to look at your spark plugs, and if you see it black and sooty like that, that's telling you there's too much fuel in there. On the other hand, though, we come over to this one. If you get it too hot, this is what can happen. This was an extended tip electrode right here, and you can see there's not much left of it right there. It's burned off. Everything's all melted off. That got too hot, and this is under detonation of a supercharged motor. That's not good because these little pieces of metal off this electrode up here end up inside the motor, and you also get detonation problems. You know, you blow a head gasket, you break a piston. There's a lot of things that can happen with that. So you don't want to be too hot either. What we're really looking for is something, this one right here, just a nice tan, light brown color. It just shows that there's no deposits building up. It's running nice and good, burning the fuel, but not sticking the deposits on it. And basically on a supercharged motor, rule of thumb is you want to go about 2 steps colder on a spark plug than you normally would. If you're using a particular heat range, just go, you know, look in the book or at your local parts supplier. They'll help you find a heat range that's slightly colder. If they start getting a little black and sooty, that's telling you the heat range is still a little bit cold, and you might want to go up one more heat range. Under mild boost conditions, 4, 5 pounds, 6 pounds, one heat range under a normal, which your car would usually use, is okay. When you really get up in a serious boost and serious motors with lots of fuel in there and making lots of power, usually 2, 3, 4 heat ranges down is what you're going to have to run. You know, another question I get asked all the time is, you know, on supercharged motors or even just general performance motors, what kind of plug gap do you run? I mean, you can't really look in a owner's manual and find a 450 horsepower small block or a 700 horsepower big block or something and find the plug gaps. General rule of thumb is when you start getting up in horsepower, you actually make the plug gaps smaller. Contrary to what people think. You know, a lot of times you'll think, boy, I got this 50,000 volt coil or 60,000 volt coil and I got this elaborate ignition system, I can really open up the plug gaps. That doesn't really work that way. You still run a small gap for a very intense spark on there. So really you can't look in a book. You could basically start a good gap to start with all the time is 35 thousandths. And then work your way down from there. If the motor's making more than about 450, 475 horsepower, you can go down to 32, 33 thousandths, somewhere in there. We get down to 25 thousandths, 22 to 25 thousandths on some really radical motors, and that's where they're just going to run at. Best way to find out, though, is when you get it, when you get your motor or you've done your modifications to it, is start at 35, take it out and run it a little bit, and then gap it down to like 32. Run it again, see what you get, then try down to 30 and run it and see what you get. And then, you know, see which way you can go. You can even try 37, 38 thousandths, and that gives you a variance. But general rule of thumb is a smaller gap on performance engines, including supercharged engines. While we're on the subject of ignition systems, how to light the fuel, let's talk about the fuel itself. What kind of fuel is good for a supercharged engine? Well, to me, a street engine runs on pump gas, 91 octane. Of course, you know, the supreme pump gas. You're not going to build a performance engine to run on 87 or 89 octane fuel. It's always the higher octane that you can get. Like out here in California, we can get 91. So 91 octane is what we want to run. You certainly don't want to go to the track and get 110 or 114 octane fuel and put it in your motor and think it's going to run very good. Because it just won't. It burns too cold and too slow. Let me kind of give you an idea what that is. Octane basically pertains to how fast the fuel is going to burn, among other things, but in easy terms, how fast it'll burn. And a lower octane fuel, like such as 87, is highly volatile. It burns real fast and it doesn't need to be compressed very much. Or let me give you an example of something else, like diesel fuel. It doesn't burn very good and it doesn't light very fast when you pour a little bit out and you try and light it with a match. It won't flash up and burn. Another one like that is alcohol. The octane rating of alcohol is up around 200. So yes, it burns, but it's not like having a cup of gasoline here and a cup of alcohol over here. If you put a match to either one, the cup of gas is going to really flare up and go. The alcohol just sizzle. In fact, you go to a lot of bars and you'll see them, they'll light them on fire and for specialty drinks and stuff, and it's not a big deal because it's not very volatile. Well, anytime you have something that's not very volatile, you need to compress it more. Blowers, you know, the static compression on a blower is low. I said, you know, 8 to 1, 9 to 1 compression max. On race motors, we get down to 7, 7.5 to 1. But we're forcing the fuel and air inside there, which makes the volume inside a lot more. So when it burns a lot under higher pressures. So we need a higher octane fuel to withstand those pressures. And let me kind of explain what's going on with this piston. If this is a combustion chamber and we have a given amount of movement right here, and it's going up and down, and it's always traveling the same amount of area. If the octane's too low or the compression's too high, what's going to happen is as it comes up, it lights and it's done about right there. Bang. That's the ping that you hear when you have too much compression or the octane of fuel is not enough. Okay, which means you either need to get a higher octane fuel or back the timing back a little bit, retard the timing to get rid of that ping. Well, that means you also lose on the power. On higher compression engines or supercharged engines, what we want to do is increase the octane rating so it burns slower. So what happens is when a piston comes up, it gets a nice long push all the way down till the piston reaches bottom dead center. That's a nice long push and that gives you the most power. The problem is you don't want to go too high in octane because what will happen is it'll come up, it'll push all the way down and it hasn't reached its full maximum ability or output to really push on that crankshaft. It really never built up the pressures that you needed. So you don't want to get too much, and I can't tell you how many times people come in and say, hey, I put 110 octane fuel in my car and I went out to the racetrack and it didn't run very good. It ran better with 100. Well, no duh, because it's burning too slow. You know, if it was just a matter of going to high octane fuel, we'd all just stick high octane fuel in our cars and go, but that's not the way it works. So we kind of have to take some things into consideration on supercharged motors. We do have a low compression, static compression, but we are increasing cylinder pressure because we're shoving more fuel and air in there. So when it does light, boom, it's a big expansion. So we want to keep it under control and keep it cool enough so we're not melting things down or detonating, but we also want that nice long push on that crankshaft to make that power that we're looking for. All right, let me kind of elaborate on what we're talking about, a slow burn. Think about pushing your buddy's car along. You know, he's stalled in a middle of an intersection, you want to push his car. You know, to get that car moving, you need to get a good push on it and give a continual, long, steady push, and that gets the car rolling. I mean, you can come up behind the car and hit it as hard as you can, as many times as you want. You're not going to move that car. It's a long, slow, steady push, and that's what's going to get the mass moving. Well, it's the same thing that's happening in here. You don't want to punch the top of the piston. That's when you get detonation or pre-ignition and pinging, and it's because it burns so fast it's like hitting it with a hammer, and that's when you break holes in the piston or break the side of the ring lands off, and that's definitely not good. We don't want to do that. Or at the least, when you're pinging, you blow a head gasket. So it's really not good to ping. Some people think, oh, I'm just pinging. That's telling you something. It says, hey, either your timing is too far forward, or your cylinder pressures are too high, or you need a higher octane fuel to remedy that. But the fast push like that, when it burns real fast, is damaging to the motor. We want that nice, long, slow push, and that'll give you the most horsepower in turning that crank, and that's what we're trying to do, is get you down the road. All right, let me show you a little problem we run into sometimes with some of these superchargers. Sometimes the intake manifold is cast in a way or machined in a way that there's not enough room right in between here, between the valve cover and the intake manifold, to actually get your valve covers in. So you want to make sure that you always do a test fit of your intake manifold and blower and even things as valve covers to be sure that everything fits, because I can't tell you how many times before in the past I've put things together and you go to put the valve covers on, you're like, oh, doggone it, doggone, not enough room right in between here to get the doggone valve cover in there. And that's a real pain in the butt, because you know the only way you can fix that is to take it all apart, take the manifold off, put it on a mill, and cut that angle in there so you can get down in there. So just check that. That's just a little tip for you. All right, well, that's about it on superchargers. I hope I gave you a lot of good information that you can use, and hopefully I put a few wives' tales to rest about superchargers not being reliable or anything. I like to arm you as much as I can with the power of knowledge, because knowledge is horsepower.